So we've looked at how we can use the general chi-square test to look for differences between the observed and the expected values in a two-way table, and to test the hypothesis that there's no relationship, or there is a relationship for the alternative, between the two categorical variables. That same chi-square statistic can also be used in a slightly different way. In this type of test, which we call a goodness of fit test, we only have a single categorical variable, and our hypothesis is that certain proportions fall into each of the levels of the category. So a very popular example is the colors of M&Ms. Lots of teachers like to do these examples where the students will look at the different colors of M&Ms and see what type of distribution you get. Well, the company at one point, I don't know if they still say this is the proportion today, but at one point the Mars company said that on average you should find 13% brown and red, so 13% brown, 13% red, 14% yellow, 16% green, 20% orange, and 24% blue. So they're not equally distributed, I guess, based on the popularity of the colors. Some are more common than others. So what we can do is take a random sample and we can test the model here and see whether or not we have good evidence that what they're claiming is true based on a random sample. So that's the idea. Your null hypothesis would be that there's a certain proportion, in this case a certain proportion that are blue, and it would be the value here in the model. That, let's see, blue is 24%, and so forth, that you have different proportions in each of the categories. And using the same chi-square statistic we talked about earlier, we can look at the expected values based on the null hypothesis that they had a certain model that's given to us. We can compare those expected values to the observed values using the chi-square statistic and get the p-value and find out whether or not the model is a good fit or not. So they call it the goodness of fit test. So, for example, in this particular example, we have 60 M&Ms, 10 of them were blue, that's 17%. That's just a sample, though. The model claims that it's 24%. This could be due to random sampling. Is there good enough evidence that it's not just random sampling, that we're going to reject the null hypothesis? So our null hypothesis, they look like this for the chi-square goodness of fit. You have a particular model that in each of the outcomes for the categorical variable, there's a certain percent here. In each category, you have a certain percent or proportion. So for the M&M example, our null hypothesis would be that there's 24% blue, that the proportion of blue is 0.24, the proportion of orange is 0.2, the proportion of green is 0.16, proportion of yellow is 0.14, proportion of red is 0.13, and proportion of brown is 0.13. Sometimes you have chi-square, like maybe on fair dice, that they're all 1/6 or something, and they're all the same, but in this case, the proportions, they're not all the same. The alternative hypothesis, you can't just throw not equals on there, because if at least one of them is incorrect, then the model would be incorrect or not be a good fit. So the alternative hypothesis, we should say it in words, it's that at least one of these claims in the null hypothesis, one of these proportions, these p sub i's for some index, is incorrect. So the idea, we're going to compare observed counts to expected counts, create a chi-square statistic, and do a hypothesis test. And in general, when you look at it, I'll do this example, but what you do, this is the percentage of the population that we're claiming would fall in that category. So we would do that percent of the sample size. So we would multiply the sample size by the population distribution in each category, which we assume is what we have in the null hypothesis. So here's our M&M example. So the claim is there's 24% blue, so if we take a sample of 60, 0.24 times 60 is what we expect to be blue, and we get 14.4. Just like in the other chi-square, even though we wouldn't expect to get a decimal value, we have to use the full digits when we do the computations for accuracy. For orange, the hypothesis was that 20% were orange, so we do 0.2 times 60. So we expect 12 orange in a sample of size 60. And you do that for each one, and so we have our table of our observed and our expected. And just like we do with the other chi-square, the chi-square test statistic is made by doing your observed minus expected squared divided by expected. And we could do that with each of these numbers, and I have the computation there. So I would do 10 minus 14.4, square it, and divide by the expected value 14.4. And I would go down each row of this table here and do that, the difference between the observed and the expected squared divided by the expected. Compute that, add all those up, and we get about 8 for this one, 8.046. Whoa, somehow my summary got really shrunk there, but I'll show you and do the summary here in the video. So we got a chi-square test statistic of 8.046. I can take my calculator and do the same thing here. Let's do second variables, get the chi-square distribution. It's number 8. Don't do the PDF. We want to do the cumulative density function, number 8. And put in your chi-square value. Always for the chi-square stuff, when you're doing it, it's an upper-tailed test. Do the chi-square value. So 8 is approximately 8.046. And then going off to infinity, and the degrees of freedom is n minus 1, the number of categories for your variable minus 1. So there were 6 colors of M&Ms, so 5 is degrees of freedom. This one pastes it, and so you can see if you don't have the menu, it would look like this. You do your chi-square value to infinity, 1e99 on our calculator, and then the degrees of freedom, which is your number of categories minus 1. Hit enter, and there we go. It's about 15%, 0.15. So what you can't read in that box there is, I was just showing, if you do this, you get a p-value of about 0.15 using our calculator. That's large for a p-value, definitely greater than 5%. So we do not have significant evidence to reject the null hypothesis. So we don't have evidence to say the model is not a good fit. Again, we never... If you look at the actual logic, we're not proving the model is a good fit. We just didn't prove that it's not a good fit. So you might say, oh, it's a good fit, but technically we are failing to reject the null hypothesis. So we did not find evidence to reject the model. Actually, I think I redid it and just forgot to get rid of the old one there. So you can see our p-value comes from doing the chi-square cumulative density function with our chi-square value 8.046 to 1e99. With 5 degrees of freedom, and we get about 0.1537. So I'll repeat it. We do not have significant evidence to reject the null hypothesis about the distribution of the M&M colors. And as I said, technically we didn't show the model is a good fit because you can never prove the null hypothesis without looking at the entire population, but we don't have evidence that it's not a good fit. And I have one more slide. Let's see. It just summarizes here. So the chi-square goodness of fit, your null hypothesis looks something like this. You have a categorical variable with, let's say, k categories, and you have the proportion in each of those is some certain value between 0 and 1. And you would compute the expected values by doing that proportion times your sample size. And then you would look at observed minus expected squared divided by expected, add that up for 1 through k here, add all of those up that you get the difference between the observed and the expected squared divided by expected. That's your chi-square. Find the probability you would get something that large or larger based on a k minus 1 distribution if you have k categories.